Hi everyone. Today we're looking at our last round of derivative rules, at least for this unit. There's a few more coming up in the next unit. We've learned power rule already, and that applies to a lot of different types of functions. And we've learned how to do some combinations of that using product and quotient rule. But there are some functions that don't really fall under that power rule, and that's mostly what we're going to be talking about today. So think about like your trig functions, your exponential functions, your log functions. These all have derivative rules too. And all of these derivative rules have been proven at some point along the way by that limit definition. So remember we talked about this. Limit is h approaches 0 of f of x plus h. You're not really going to need this for these notes, so you don't have to worry about copying this down. But so someone somewhere took each one of these functions and did this process with them, and then was able to simplify this algebraically to prove that the derivative is always whatever I'm about to show you, okay? Those proofs are a little bit above the level of where this class is. That's like a master's level class in analysis is what that's called. So you don't have to know why these are what they are, but I just want you to know that no one's like making these up. I didn't make these up. There isn't some mathematician out there somewhere that just decided these were going to be the derivatives. Mathematically, this would be why they are the derivatives. So this first one we looked at a little bit when we did the activity in class where we were like drawing derivatives. And we should have noticed that when we took the derivative of the sine function, what we ended up with was the cosine function. Okay. And that's because if you think about what the sine function looks like, it looks like this. Well, it should be a little more symmetric than that, but so that's a really terribly drawn sine function. But if I put all my zeros in place, so right, this would be a derivative of 0, this would be a derivative of 0, here would be a derivative of 0, all my bumps, right? And then think about, like, for example, I'm increasing from here to here, so my derivative would need to be positive. Decreasing from here to here, so my derivative would be negative. What I get, if you look at this graph in purple, is an also poorly drawn version of the cosine function. Okay, so cosine is the derivative of sine. So then, of course, the question is, does that work in reverse? Is the derivative of cosine just sine? And it's close. If you look up here, all of the zeros are going to be in the right spot. So everywhere that the cosine has a maximum or minimum, the sine function is going to be hitting 0. So like right here, this minimum would correspond with this 0. So all the zeros are right, but your increasing and decreasing intervals are not. So for example, on the cosine function, between here and here, you're increasing, so you would expect the derivative to be positive, but the sine function is negative. So what we really need is like this sine function, but flipped upside down. And so the way that we flip things upside down is we put negative signs in front of them. So the derivative of cosine is negative sine of x. Okay, these next few I'm not going to try to draw for you. These ones are just straight up, like you might need to bust out some flashcards and memorize them. The derivative of tangent is the secant squared function. And then we have derivative of cotangent. So tangent and cotangent kind of go together, right? Similar, well, not really similar, but I mean, the derivatives are going to work the same way the sine and the cosine functions derivatives do. Cotangent is also going to get a negative sign in front of it. And instead of secant squared, it's cosecant squared. Sorry to make that an E there. Okay, but negative cosecant squared is the derivative of the cotangent function. These next two are super weird. The derivative of secant is secant x, almost its own derivative, multiplied by tangent of x. And so if you look at kind of the pattern that we have established here, these two kind of go together, right? One's positive, one's negative, and they're just, you know, kind of sister functions here. Same thing here, these two sort of go together. One's positive, one negative, and we've got secant versus cosecant, which is really a difference of sine or cosine. So using that pattern, you may be able to figure out what cosecant is going to look like. the cosecant of x's derivative is negative cosecant x times cotangent of x. So these two also go together. So do you have to have these memorized? Yes. Yes, you do. But I would really focus on like sine, tangent, and secant, and then the other three kind of fall in line. If you can remember those, then these just kind of piggyback onto those ones that you have memorized. Okay, let's talk about our exponential functions down here. This was another one that we drew a graph of previously. So just to remind you what that would look like is if you have an exponential function, looks like that, and I ask you to draw me what the derivative would look like. Well, over on this side, your derivative is going to be awfully close to 0, right? You're going to have, they're all positive because this is always increasing, but you're going to be really close to 0. And then as you move to the left, your derivative is tilting upwards and it's getting bigger, faster, and faster, and faster. What kind of function does that sound like to you? It's a function that's close to 0 but positive, and then gets bigger, faster, and faster, and faster, and faster. Okay? The exponential function's derivative is just another exponential function. Now sometimes it curves a little differently than the original function, but there is one particular function where the original just matches the derivative. It's its own derivative. And that's this one. That's our old friend e. So the derivative of e to the x, this is one of our easiest ones to remember, is just e to the x. This one, if it's something other than e in the base, the derivative starts out the same. So it starts as a b to the x. But then you have to multiply by a natural log of whatever that b number is. Okay? And again, that just impacts like how sharply this thing curves. You know, depending on the curve of the original, the derivative graph might look different too. Okay, our log functions, just like e to the x was kind of a special unique case, natural log of x is also kind of an easy one. It's not as easy as this one where it's just exactly the same, but the derivative of natural log of x is 1 over x. To kind of confirm that for you, here's what your natural log, or any log, right? This looks like a log function over here. The derivative then would be, they're all positive, right? This whole thing is increasing, so my derivative is always going to be positive. These start out really high, right? This is a really steep slope, so I'm going to start up here someplace, probably way up here. And then slowly they start to flatten out and approach 0, but it never turns around where it's heading in a negative direction. So it's going to approach 0, but never cross 0. And that's going to look like your old friend the hyperbola, which is 1 over x. Just like up here with the b to the x versus the e to the x, when you have a log of some other base besides e, your derivative there starts the same way. It starts as a 1 over x. But then in that denominator, again, you're going to multiply by the natural log of whatever that base number is, whatever b is. Okay, so you're responsible for these rules. The next page covers some examples. I'll probably start that in a second video. But I would recommend maybe some flashcards for these, something so that you can memorize these. You're going to use most of them so often that you're going to remember them eventually. But if for right now you're struggling with that, I mean, of course, flip back and look at your notes as you're working through the examples. But do make sure that you're doing something to make sure you memorize these values.